So we're talking about secants and tangents, very popular words in geometry. We started this last week, so I'm going to go over this, a little quick review, and then we'll complete the lesson. We'll do some examples. Now, a secant, as you can see right here from the figure, is basically a line, okay, that intersects at exactly 2 points in a circle. So even though I have this secant right here, it's nicely labeled, that would be a secant. That would be a secant. This could be a secant. This could be a secant. As long as it's a line that intersects, that goes through 2 points, okay, of the circle, then it's going to be a secant. Let's go ahead and, sorry about that. Okay, now the tangent. A tangent is a line that intersects a circle at exactly 1 point. So again, even though I just have one tangent drawn out here, this would be a tangent. And that would be a tangent. And this would be a tangent. And this would be a tangent. Okay? It's a line that intersects at 1 point and 1 point only. Does that make sense? Okay. Now, the intersection point of the tangent line in the circle is called the point of intersection, or the point of tangency, or the point of contact. Okay, so it's very simple. This guy right here is the point of contact, because the line contacts the circle right there. It's the point of tangency because it is tangent to that circle at that exact point. And it is the intersection point. It is where the line and the circle meet. Make sense? Okay. Okay. Now, there's a postulate that involves tangents and radii. Okay? When you have the point of tangency that is created from a tangent line right here, okay, and the radii, you are going to create a 90-degree angle. It says here the tangent of a circle is perpendicular to the radius of the circle it is tangent to. So whenever you have a circle and they say that a line is tangent to that circle, if I create a line, a segment from the center to that tangency point, and I create a perpendicular line, a 90-degree angle, then I am proving that that line was tangent to the circle. Yes, sir.
Would a line, see that line in the middle, would that also be a 90 degree?
Yes, sir. The question was, okay, this line here in the middle, if that's the radius, and if this is tangent to the circle, then I will be creating a 90-degree angle right there as well, sir. Okay, the central angle. What about the central angle? Would this central angle be 90 degrees? It really depends. This central angle here, it really depends. If this is a straight vertical radius and this is a straight horizontal radius, then yes, it will be a 90. But unless those are both horizontal and vertical, we cannot determine that, sir. Okay? That makes sense, everybody? So, again, the point of tangency between a radius and a tangent creates a 90-degree angle. They are perpendicular. Does that make sense? Okay. Let us continue now. Now, we just talked about tangents and secants. Now we're going to investigate tangent segments and secant segments. A tangent segment is basically a tangent, but it's only a segment. So that means one of the endpoints is outside of the circle, but one of the endpoints is the actual point of tangency. How can I prove that that's a tangent segment, Moral? Well, if I take the center and I follow my radius to the point of tangency, if I create a right angle there, if they're perpendicular, that is proving now that this is a tangent segment. Does that make sense? Okay. Now, There was a question, what if you have a straight line just like this guy right here? Is that a tangent segment? Yes or no? In this case, you have two tangent segments. You have tangent segment 1, which is from the point of tangency to this external point. And then you have tangent segment 2, which is the tangency point to this external segment. So you would have two different tangents in that particular case. This would be basically two segments combined. And the central point here, the point of tangency, that's going to define whether or not I go to tangent 1 or I go to tangent 2. Does that make sense? Okay. Now, secant segment. A secant segment is a secant, but it is only a segment form. It is not a line. It does not continue forever. The whole entire length, okay, from the endpoint to endpoint, that whole entire distance is called the secant segment. But there's an internal and an external part. The external part is literally the external part. It is part of the secant segment that goes from the edge of the circle all the way to the external part away from the circle. What's left inside is basically a chord. That's the internal part. But they don't really discuss the internal part that much. They discuss the external part of the secant segment quite often. Yes, sir.
On the other one, go up for a second.
Okay.
Describe the whole segment, all segment.
Okay, I didn't understand it. Can you describe the whole segment as a whole segment?
Okay, yeah. You have it divided into two, like the two parts.
We're talking about the tangent segment up here?
Yeah.
Okay, we already talked about this. So thank you for not listening. Apparently you did not. Apparently you did not understand, because then you're asking me again. So what are you asking?
You know how you divide it into two?
Yes.
With endpoints, if you, would that be a whole segment?
Full tangent segment with
Yeah.
two endpoints that are outside.
Okay. Again, you did not listen to me. The question was, is this one whole tangent segment? The answer is no, because a tangent segment is defined by one of the endpoints at the point of tangency, and then the other endpoint on the external part of the circle. So this would be one tangent, and this would be a second tangent. You cannot have them together as one tangent. Does that make sense? Thank you, sir. Now, does that make sense, guys? External part of the secant, that makes sense? The whole secant segment is the whole entire kit and caboodle? Yes? Okay. Now, almost done. Theorem 85 states that if two segments are drawn to a circle from an external point, then those segments are congruent. It's called the two-tangent theorem. It's called the two-tangent theorem. If you've got this external point, let's say, got this over here, okay? And I draw two tangents here. Since these two tangents came from the same external point, this guy must be congruent to that guy. Always.
No matter what,
Come again, sir?
no matter where it's drawn from.
The question was no matter where it's drawn from? Yeah, let's say I have a point here.
Where the line is drawn.
As long as I have, that won't work. It's got to be tangent. Okay, so right here, right here. If this guy is a tangent and this guy is a tangent and it's coming from this center, from this external point, that's congruent to that. Does that make sense? You sure? Okay. Awesome. Let us continue then. Now, we know we've talked about tangent lines. Okay, tangent segments, secant lines, secant segments. Now we're talking about tangent circles. Hopefully you've realized that tangent is referring to an intersection at one point. So when you're talking about tangent circles, sorry about that. Okay, so when we have tangent circles, we're talking about circles that intersect each other at exactly one point. And you can have an internal or external tangents when you're talking about tangent circles. Okay? The external tangent over here, okay, is this point right here. Now, why is it the external? Okay, yeah, I got a hand up. Very good response. Why is it external? Because it's on the exterior of both circles. I couldn't have put it better myself. Very well done, son. This point is on the exterior of this circle, and it's also on the exterior of that circle. So therefore, it is this guy here is the external tangent. Well done. Very nicely done. The internal tangent is a little bit different. If you can see here, you have a smaller circle within a larger circle, and they are both tangent at one point. But since the small one is within the large one, doesn't that make sense that it's an interior tangent? Because the small circle touched the large circle on the interior of the larger circle. Does that make sense? Promise? Okay. Okay. May I continue? Okay. One more thing and then we get to actual problems, okay? Now, we talked about tangents, we talked about secants, we talked about tangent segments, secant segments, we talked about tangent circles. Now we're going to talk about common tangents. Common tangents are a little bit different than a normal tangent. We know that the definition of a normal tangent is a line that intersects a circle at exactly one point. Well, a common tangent, okay, is going to be a tangent that intersects two or more circles at exactly one point. So let's look at the three different lines that I have here. First of all, PQ is the line of centers because I went from the center of circle P to the center of circle Q. That is just called a line of centers. That is not a secant, that is not a tangent, that is not a common tangent, that is nothing. It is simply a line of centers connecting one center to the next. Now, let's look at XY. XY is called the common internal tangent. Now, this may be a little bit confusing. In fact, let me split the screen so you can see what I mean. In this particular case here, internal was when one circle was within the larger circle. External was when both of the tangents hit the exterior of both circles. But now, look at the blue here though. It would look as if that would be an external, correct? So why do you think it's called internal? Thank you very much. Fantastic. It is an internal because the line is in between both circles. Very good job, son. Awesome. Very well done. And then, my last but not least, my AB is the common external tangent because it's on the exterior. It's on the outside of both of them. So when it's in between, like XY, that's a common internal tangent. When it's on the outside of the circles, then that's a common external tangent. Again, the reason why they're called common is because it's one tangent line that's tangent to two circles. So it's a common line that becomes a tangent for both. Is that clear, y'all? Make sense? Okay. May I continue? Thank you. Okay. So let's continue. Given XY is a common internal tangent to circle P and Q. That makes sense. This is my xy right here. That makes sense, hopefully. Okay. XS is tangent to P. XS is tangent only to P. Now, if you think about it, you may be saying, wait, hold on, Moro. Wait a second. It touches Q2, Moro. You're wrong. That's a tangent. Why is that not a tangent? Because that is not going to form a 90-degree angle. Very good job. Awesome. Okay, so XS is a tangent to circle P, and YT is the tangent to circle Q at point T. So the first thing we're going to do is put all these givens, okay? Let's go ahead and just make our lives easy. And again, XY is a common internal tangent. XS is tangent to P, and YT is tangent to Q. Yes, sir. Okay, sorry about that. So we got all of our givens, okay? Now, what can we tell from here? Yes, sir.
XS is included in X prime because of the two tangent theorem.
Phenomenal. I was told that XS is congruent to XY because the two tangent theorem. Phenomenal. Yes, sir.
YX is YT.
Next, XY is congruent to YT because also the two tangent theorem. Is everyone seeing this? XS is congruent to XY because of the two tangent theorem. Okay, again, we apologize about that interruption. It's been a lot of interruptions today. I apologize. Okay, so we had stated that XS is congruent to XY because of the two tangent theorem, right? And then we also said that XY is congruent to YT because of the two tangent theorem. Again, here's the external point. It's tangent. Boom, they got to be congruent. So now, what do we got, my man? XS is congruent to YT because of transitive property. That's exactly right. Awesome. Does that make sense, y'all? Fantastic. Okay, now, in this particular case, let's check out what we have. They tell us that it's a radius is 8. So that means this is 8 millimeters. They tell us that the tangent segment is 6 millimeters. They want to find OP. Someone said Pythagorean theorem. They are correct because I have a radius and I have a tangent, so that creates a 90. But better than Pythagorean theorem, it would have been better to know that this is a 3, 4, 5 triangle times 2, so OP would be 10. Knowing the Pythagorean triples helps you out immeasurably. Does that make sense? Okay. Number 3. Now in this case, they tell us the following. They say here, why is this? Okay, there we go. They tell us here that a circle with radius of 8 centimeters is externally tangent to a circle with a radius of 18 centimeters. They want to find the length of the common tangent. So they want to find the length of AB. Now, this is very simple if we remember some of our core knowledge. Let's make this easy for you guys. What kind of an angle is formed here at QAB? A 90, very good, thank you. What kind of an angle is formed here at PBA? A 90, very good, thank you. Now guys, if you think about this, wouldn't AB, that distance, okay, have to be equal to the bottom distance if I created a rectangle? So if I created a rectangle and from here to here is 8, then from here to here would also be 8, correct? Then from here to the center would be 10, correct? Well, draw a straight center line here. Think about this. This is really, 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 really simple. If this is 8 and this is 8, okay, what is AB going to be? What is this guy going to be right here? Well, no, think about it. From Q to here, what is the radius? 18. From the tangent point to here, that's 8, right? So don't I now have a triangle that's like this? 10, 26. So wouldn't that be a 24? This is a 5, 12, 13 times, that's a 5. 5, 12, 13 times 2. Okay, look guys, 10, that's a 90, that has to be a 90. The radius here is 18. This radius is 8. So this distance here is 26. So isn't this a 5, 12, 13 times 2? 5 times 2 is 10. 13 times 2 is 26. 12 times 2 is 24. So what does x equal? 24. Okay, I know that some of you just said, I never thought of that. I know, that's why I teach it. So you could think about it. Use the relationship between the tangent and the radius. The 90 degrees, that's what gives you the key here. Right there. That's what gives you the key. Okay, and also realizing that I got this distance of 26 simply by doing a radius plus another radius. Does that make sense? Okay, no? Okay. I had a big fat no here. So what we're going to do is we're going to erase it. We're going to do it again. Okay. Let's start fresh. Everyone agreed that it said that one of the radii here is 8 millimeters and the other one is 18. Is everyone with me there? Does everyone understand that QAB is a 90-degree angle because you have a radius and a tangent that connected? Does everyone understand that PBA is a 90 because you have a radius and a tangent that connected? Does that make sense to everybody so far? Okay. Now, I know that if I create a straight line here, from here to here, that's 18, correct? And from here to here, that's 8, correct? Okay. Well, this is what I thought. I know that QP is not the same as AB, so I cannot just call that 26 because they're just not straight lines. But what I can do is, well, if this is a straight line, and this is a straight line, and then this is a straight line, right, because of the 90s, correct? Can't I just cut up at an angle here and make a rectangle? So if that's 8, this is 8. If that's 8 and the whole entire radius is 18, wouldn't this be 10? So now look at what I have here. If that's 90, this is 90. This is 10. This whole thing is 26. So isn't this a 5, 12, 13 triangle times 2? 2 times 5 is 10. 2 times 13 is 26. So 2 times 12 is 24. So if that's 24, AB is 24. Talk to me. Thank you. 26 is going to be the hypotenuse. Yes, sir. Isn't that across the 90? Thank you. I appreciate your question. Yes, sir. You got it? Excellent. Does that make sense to everybody? Promise? Okay. Let's go. Let's do another one. Last one. Okay? Now, in this case, they give me this figure here, and they say it's a walk-around problem. They say that each side of a quadrilateral, ABCD, is tangent to the circle. Okay, so they've got here, let me label the points. They've got A, B, C, and D. And they say that AB is tangent right here. BC is tangent right here. CD is tangent here. And AD is tangent there. They tell me that side AB is 10. BC is 15. AD is 18. And they, oh, wrong one. AD is 18. And they want to find CD, which is X. Go ahead and write this down. It's going to be a lot easier than you think, I promise. It's going to be a lot easier than you think, I promise. Correct, son. Let me show you how exactly it works. Someone just finished saying, isn't this just a two-tangent theorem? It is. Let me go ahead and make our lives easy. Let me first clone this sucker so that I can have something to work with here. And let me go ahead and reduce this guy. Okay. Now, let's go ahead and get rid of this. Okay. We know already that sorry about that. We know that BC is 15, correct? So could we call from B to point tangency, could we call that X? Then what would we call from the point of tangency to C? 15 minus X. Now watch. Isn't this the two-tangent theorem? So ain't that X? So that, no, well, on this side it'd be 15 minus X, correct? Does that not make sense? Now, pay attention to this one. On side AB, the whole thing is 10. If B to the point of tangency is X, point of tangency to A is 10 minus X. You with me? So then this is 10 minus X. You feel me? So now the only thing we got to figure out is from point of tangency to D. How, well, what do we know about huh? Well, this is X and this is X because of the two-tangent theorem. This is 10 minus X and that's 10 minus X because of the two-tangent theorem. No. AD is 18, correct? AD is 18. But if from A to the point of tangency is already 10 minus X, what would the point of tangency to D be? 18 minus 10 minus X. So then this part over here is 18 minus 10 minus X. Why isn't it just X is the question. It's not just X because AD is 18, son. So if this little piece from here to here is 10 minus X, and the whole thing is 18, then this little piece is the 18 minus the 10 minus X. It's a great question. Thank you, son. So now, what do we do? Hello? I want to find CD, so I got to find what X is. How do I find out what X is? Hello? What do we do here, guys? Doesn't CD here, guys, equal 15 minus X plus 18 minus 10 plus X, gentlemen? Does that not work out for you? Don't the X's cancel? 15 plus 18 is 33 minus 10 is 23. Talk to me. Does that make sense? Are you sure? Okay. Awesome.